Okay, here we go with section 3.2 on compound and continuous interest, and hopefully the sound is right this time. So we'll start with some formulas and then do some computations with formulas. So problems 1, 3, well, a whole bunch of them are just sort of wrestling with formulas a little bit. A handful of word problems, and finally annual percentage yield. And at the end, we'll do a little bonus video deriving compound interest formulas and an explanation of where the continuously compounded interest formula comes from, and sort of what is E and why do we care about it. So what are the formulas? We've actually seen these from section 2.5. Unlike test 1, you have to memorize these for test 2. In fact, the College of Business insists that you have these memorized before you leave this class. So compound interest, A equals P 1 plus R over M to the MT. Continuously compounded interest, A equals P e to the RT. These are both exponential functions. This is why we need logs, right? As logarithms allow us to solve exponential functions. So what are the variables? A is the amount in the account sometime in the future. P is the principal. That's how much you invest to begin with. R is your interest rate. That has to be a decimal. M is the number of times the interest is compounded per year. That shows up in 2 places. And T is time, and that's in years. Now we can write a slightly different formula for the compound interest formula. If we write I as R over M, so that's this thing, that's the interest per compounding period. So if you get 12% interest a year, if your rate is 12% a year compounded monthly, then that's 1% each month. N equals MT, your exponent, that's the total number of times interest is compounded. Again, if you for 10 years and it's compounded monthly, that's 12 times a year for 10 years, 120. So you can shorten this formula a little bit as A equals P times 1 plus I quantity to the N. If we make this I and this N. And these I's and N's, they'll show up again in sections 3.3 and 3.4. Okay, so those are the formulas. All the problems in this section pretty much follow the same format. You have to figure out which of the 2 formulas you want to use. If it says continuously compounded, you use this one. If it doesn't, you use this one. And they'll give you all but one of the variables, and then you try and solve for that missing variable. So, for example, example 1, compound interest. A is 4,500, R is 8%, compounded weekly, T equals 39 months. Then what is P? Well, the formula we're dealing with, compound interest, is A equals P 1 plus R over M raised to the MT power. And we've got 5 variables here that we need to know about. What do they tell us here? A is 4,500. That's the amount later. R is 0.08. Remember, 8% has to be a decimal. T is 39 months. 39 divided by 12. 39 months is divided by 12 to convert it to years, and so that's 3.25. So 39 months is 3 years and 3 years and 3 months. And M is compounded weekly, so that means 52 times a year. So plug everything in. The only thing we're missing is P. So 4,500 equals P 1 plus 0.08 over 52. 52 times 3.25. Generally, if you're putting this in your calculator, calculate that first, add the 1, and then raise to this power. Make sure you put a parentheses around that so the calculator knows that 52 times 3.25 is the power you want. And if you grind all that out, you should get 4,500 equals P times this whole thing, which should become 1.2967 ... right? Lots of decimals. And divide 4,500 by this number, and you get 3,470.43. So if you invest this much now and let it sit for 39 months at 8% compounded weekly, then you'll end up with 4,500. So standard format. There's a formula. They give you all but one of the variables. Figure out what that last variable is. So, example 2, for continuously compounded interest, oops, Scrolled by a little bit too fast. For continuously compounded interest, if A is this, P is that, and R is that, what is T? So continuously compounded interest is that formula. What variables do they give us? Remember that E here, that's not a variable, that's a number. It's 2.7 something. It's the base for natural logarithms. A, they tell us, is 3,000. P, they tell us, is 2,000. R, they tell us, is 0.03. T, we don't know. Okay, so we set everything up. 3,000 equals 2,000 e to the 0.03 t. Got a t, the variable that I want to solve for, it's up in the exponent. How do I get things down out of the exponent? That's what one of the log rules does. Right? It takes exponents and turns them into coefficients. So the first thing we got to do is isolate this term. So we'll divide both sides by 2,000 to get 3 halves. The thousands cancel out. Equals e to the 0.03 t. Great. So 3 halves, right? That's 1.5. So we're just write that as 1.5. Now I can take log of both sides. Natural logarithm of 1.5 is natural logarithm of e to the 0.03 t. One of the things we saw on the worksheet was that log of e to the 0.03 t, that's just the exponent. So technically, log of 1.5 equals 0.03 t log of e, right? The exponent comes out, the power comes out as a coefficient. Log of e, though, this thing, that just equals 1 because it's e to the 1. So log of 1.5 equals 0.03 t. And so time is log of 1.5 divided by 0.03. There's a point there. And that is 13.52. And time is always in years. Okay. So, example 3. Right? Again, this is a how long question, right? So we're going to need logarithms to solve this. Compounded monthly. So this is this formula. It's not continuously compounded. And we want to know what are our variables. So we're investing $5,000. The amount you invest is the principal. 3% interest, so that's your rate as a decimal. Compounded monthly, 12 times a year. How long? Well, we don't know that, but we want to know, we want to have 12,500 in the future. We don't know what t is. Great, so we know all the variables except one. We plug them all in. And we get that. This is a 3. So, again, we're looking for the variable in the exponent. We have to use the log rule. What we need to do is isolate that part, and we'll do that by dividing by the 5,000 first. And so that gives you 12,500 divided by 5,000, which is 2.5. 0.03 divided by 12, that is 0.025. So this thing inside the parentheses becomes 1.025, quantity to the 12t. And now we can solve for t. How do we get this out of the exponent? Take the logarithm of both sides. To the 12t, like that. And now logarithm of something raised to the power can come out front as a coefficient. So log of 2.5 equals 12t times log of 1.025. Okay. Now keep in mind that this thing here, this is a number, whatever it happens to be. This is a number, whatever that happens to be. You can, at this point, if you want, just calculate these things and put in the decimals. I won't. I'll just finish this off using the logs. So this is a variable t times this number times this number. So to get the t by itself, we'll just divide both sides by 12 times log of 1.025. right? And then the 12s cancel out, these logs cancel out, and we're left with t equals log of 2.5 over 12 times log of 1.025, and that comes out to be about 3.09. You know, there's more decimals, of course, but if you round it off, that should be about what you get. So, right, these kind of how long problems, how long will it take to increase to a certain amount, involve logarithms, and it's the rule that takes a power and turns it into a coefficient. That turns out to be the most useful of the log rules for us anyway. So word problems are also actually the same as all the problems we just did, because there's a formula. They give you all the variables except one, and you need to solve for that one. So Bob is saving for a boat. He has $5,000 put away in his account that earns 1.2% compounded monthly. How much will we have in 7 years? Compounded monthly, so that means it's not compounded continuously. So we need to use the compound interest formula. And I always just list all my variables like this so that I know what it is that I've got and what it is that I'm looking for. He put $5,000 away, so that means he invested that principal. 1.2% is my rate, so that's 0.012 as a decimal. Compounded monthly, 12 times a year, and he lets it sit there for 7 years. And what we don't know is how much he has there. So you plug everything in. A equals 5,000, 1 plus 0.012 over 12 to the 12 times 7. Little parentheses around that. Great. So plug everything in, calculate out what you get, and it should be 5,437.92. 1.2% is not a lot of interest, so over 7 years he only gets $437.92 in interest, right? So if you look at his account, there's the 5,000 he put in it. The excess over that is the interest. So we might as well just make that a little note. Right. So the amount in the account is your 5,437.92. It's the amount you put in, that's how much you invested, 5,000, plus whatever you earned in interest. So that's the 437.92. Okay. So most of the word problems just are like that. You know, they give you a formula, they give you a situation, you have to figure out which formula to use, the continuously compounded interest or the compound interest, and then they give you all but one of the variables and you have to solve for that variable. So APY, now this is an interesting concept because for a particular amount of money they invest, the APY is, this is the definition, the simple interest rate that yields the same amount as interest in the investment. And what that allows us to do is it allows us to compare investments that have different interest rates, so a higher interest rate is better, and different compounding rates, again, more often is better. And the problem is, this has got, of these three investments, this has got the highest interest rate, but it's compounded least often, right? This is compounded most often, right? But it's got the lowest interest rate. So which is the best? And what is the APY for that? So how do you compare interest rates? How do you compare accounts? Well, the easiest idea is to say invest $100 in each account for 1 year. See which is best, right? So A, is compounded semi-annually. A equals P1 plus R over M to the MT. And here we want A, well, we want to see how much we have after 1 year. We'll invest $100. The rate is 0.05. M is twice, semi-annually, that's twice a year. And T is 1 year. So for A, we get A equals 100, 1 plus 0.05 over 2 to the 2 times 1. And if you grind that out, you get 105.0625. Okay. What about B? Well, still same formula because it's compounded monthly. A, we don't know. P, again, we're just investing $100 to see how much we would get. Interest rate here is 0.0495. It's a little bit less than that one. M here is 12. This is compounded twice a year. This one's being compounded 12 times a year. And T is still 1. So, if we invested $100 into this account for a year, how much would we get? Well, $100 at 0.0495 interest 12 times a year in 12 times 1. And you grind that out, and how much do you get? 105.0639. And then finally, C. Oh, let's go back up and take a look at C. It's 4.93% compounded continuously, so we have to use the continuously compounded formula. Right? A, we don't know because we want to know how much we'll have if we invest $100 at the end of the year. E is not a variable, it's a number. R here is 0.0493. And T is 1 year. Great. So, how much do you have? 100 times E raised to the power 0.0493 times 1. And so you'll have $105 and 0535 cents. So, great. So now we've calculated how much we'll have in each of the accounts after 1 year. So, let's actually do a little table here. Account A, that one was 5% semi-annually. And at the end of a year, you'll have $105 and 0.0625 cents. B was 4.9 for 5%, compounded 12 times a year. And that gave you at the end of a year $105.0639 cents. And C was 4.93%, compounded continuously. And I'll explain in a little bonus video why it's called compounded continuously. And that gave us $105.0535. Great. So, which is the best? Well, this is the best. Not by a whole lot over that, but by a bit over that. And of course, this is only if you're investing $100. If you're investing $1 million, right, or $1 billion, you start running into some money. So, this is the best. It gives you the most money. This is the worst. So, what is actually the interest on this? Well, you invested $100 and you got interest of 5.0625, right? And this is the best, but what was the interest there? $5.0639 in interest, and the continuous compounding gave us $100 plus $5.0535 in interest. So this is how much you invested. This is how much you got in interest. Interest, investment, investment, interest. Okay, so APY. What's that? Well, if you invested $100, right, and you just did interest at the end of 1 year, what would your interest rate have to be to get you this much? Well, $100 at 5.0625% simple interest for 1 year. That would give you, big surprise, $5.0625 in interest. Right? So, what is a way to interpret these results? This is how much you get from investing $100. And so it's the effective interest rate if it was just simple interest. So this account, 5% 2 times a year, is equivalent to getting 5.0625 once a year. 4.95% 12 times a year, that's equivalent to getting 5.0639% once a year. 4.93% compounded continuously, that's the same as getting 5.0535 once a year. And so what this APY does is it brings everything to what would be the interest rate compounded once a year. Compounded once a year. The same amount of interest as your investment. So that's what the APY is. And so what it does is it allows you to compare by standardizing the period, it allows you to compare different investments, right? So if you see APY of 5.0625 and APY of 5.07, right, then the 5.07 is better, regardless of how many times it's being compounded, or those specific details. So what's the easiest way to compute the APY? Well, the book has a formula, right? But this is how I always calculate it, right? You just calculate what the how much interest you get on $100, and that is going to be the APY. That'll be the interest rate. But there is a formula that, if you want to look it up in the book, you can. And so that is the end of that, except for the bonus video. Yay, everybody loves bonus videos. What's the derivation of these formulas? So the compound interest formula, A equals P1 plus R over M to the MT. Where does that formula come from? Well, let's look at, just to make our life a little bit easier, suppose we invest $100. Oops, that should be $100 at 12% interest compounded monthly. Right? And so what I'm saying here is P is 100, R is 0.12, M is 12, and so that makes my life a little bit easier. R over M is 0.12 divided by 12, so that's going to be 0.01. You're getting 1% a year, 1% a month. So we'll set up a little table. Well, we'll run through a little bit. Suppose you invest $100 in January, right? And it sits there. We assume that you get your interest is compounded at the end of each month. So how much do you have in your account? Right? You have $100. So in February, right? You've got your $100 in your account. You get interest though. So this is your first compounding. How much interest do you get? Well, you get 0.01, right? 1% interest every month, right? Because you're getting 12%, 12 times a year, so that's 1% each time. So the interest you get is 100 times 0.01, right? Which is 1, but we're not going to actually worry about it too much, because the amount in the account is the $100 that you had from previous, plus this interest, which is 100 times 0.01. And the reason why I'm not multiplying this out is because I want to actually factor out my 100 here and say that this is 1 plus 0.01, or the amount in your account is 100, which is your principal, right? That's the P times 1.01. Excellent. And that's after your first compounding. In March, is your second compounding. Right? How much interest do you get? Well, you take your amount that's in the account, which is $100 times 1.01, that's the amount in the account, and you multiply it by 0.01. Awesome. So now how much do you have in the account? Well, you've got the amount that you had at the end, the balance from the previous time, and you have your interest, which is this. Interest is this times 0.01. And now I can do the same thing that I did before. I'm going to factor out the amount that was in the account previously, the old balance. So if I factor these two out, what's left behind is, well, a 1 from there and a 0.01. And this is not a 1, that's a parentheses. So I get 100 times 1.01 times, well, this is another 1.01. Right. These two, that was the previous balance, this is the effect of the interest. So after two compoundings, what do we have? A equals 100 1.01 quantity squared. And in general, if A is the amount in the account, how much we have in the account after one compounding? We have that plus the interest, right? So if you have A is the amount in the account, then when you compound the money, how much do you have in the account? Well, you have the amount that you had plus whatever interest you got. Factor out the A, what are you left with? A times 1 plus 0.01, which is 1.01. Right? And we're seeing that over and over again here. Right? We start out with this amount. How much do we have after one compounding? We have the amount we had in the account before times 1.01. What about after the second compounding? We had the amount we had before times 1.01. And so every time you compound, you're essentially taking the amount that's in the account and multiplying it by 1.01. So after n compoundings, how much do you have in the account? Well, the amount in the account is the amount of your initial investment, and each compounding, you multiply that by 1.01 to figure out how much you get. 1.01. And so after n compoundings, how many of these are there? Oops, don't want to actually go that far. N compoundings. Well, the whole point of multiplying something of exponential notation is if we multiply something by itself n times, we can write that in a particularly nice way. Oops. Running out of space here, that's okay. So A equals 100 1.01 to the n. But remember that this is 100, oops, it's not erasing well, there we go, 1.01 to the n. This is 100 times 1 plus, well, the 0.01, right, that was our r over 12, because that was our m, and n is the number of times you compound it. So if you're doing this 12 times a year for t years, n is going to be 12t. And so that's really our formula. And you can, go through the whole thing and replace the 0.01 by an r and the 12 by an m, and you get the same thing. So that's how that works. And here's a little table. Why is it called continuously compound interest formula? So what we're looking at here is, what is this table? Invest, let's see, $1. So what is this table? Invest $1 at 100% interest, which is, of course, not possible, but it's a mathematical problem. We just want to see why it's called continuous compounding. Okay, I think it decided to save something there. Reacting a little slowly. At 100% interest for 1 year. Okay, so how much would you have at the end of the year if it's compounded yearly? Well, that's just once. You'd have $2. So for all of these, right, the formula we're using is A equals 1, because that's our investment. 1 plus 1 over m to the m times, well, 1, because it's 1 year. So we'll just leave it as m. So 100%, that means r is 1, so that goes there. So we're looking at this number, and that gives you the amount. So if it's yearly, you end up with $2, right? If you're getting 100% interest paid once a year, then at the end of the year you get you get $2. If it's semi-annually, you get 2.25, because you get 50% halfway through the year, so then you have $1.50, and then you get another 50%, so 75 cents in interest at the end of the year. That gives you 2.25. Quarterly, 4 times a year, you'll end up with this much. Monthly, 12 times a year, you end up with this month, 52, 365. Hourly gives you this much. Every minute gives you this much. Every second, that gives you this much. It turns out that if you compound as often as possible, you don't end up making huge amounts of money, right? There's actually a limit to how much you can actually do it, right? And if you compound every second, the amount you get is this number. And that is, of course, our friend, the number E. So if you compound every second, you can start compounding every half second, millisecond, billionth of a second, etc. But you'll never actually be able to do better than compounding continuously. So if you ever take calculus, what you find, well, what you prove, or see as a definition, is the limit as m goes to infinity, so compounding often enough as all the time, continuously, of this thing equals E. Right? And so the interest you get, if you compound as often as you can on $1 at 100% for 1 year, the best you can do is actually get E dollars back if it's compounded continuously. And this can be modified if we change 100% to some interest rate R, you get e to the R. And so that's why it's continuously compounded is called that, is because it's, if you compound all the time, every instant, what interest do you get? And you take this formula and you take the limit of it and you end up with that. And we're not going to get into limits and how that exactly works.